Myself, Benilda, Assistant Professor in the Department of Artificial Intelligence and Data Science at Sri Muthukumaran Institute of Technology. Today, we are going to see the subject 3D Printing and Design. The subject code is CCS331, Regulation 2021. Already, we have seen 3 units. Today, we are going to start with 4th unit, Laser Technology. So, the first topic is principles of laser. So before getting into the principle, first of all we can see the abbreviation for this laser. So light amplification by stimulated emission of radiation, it is the abbreviation for this laser. Next one is principle. The basic principle of this is a laser works on a principle of stimulated emission of radiation where atoms are excited to a higher energy state and then induced to emit coherent light photons. Next, the characteristics of this laser light. It is monochromatic, coherent, directional, and high intensity. Next, the applications. Wherever we are using this light laser. In laser printers, laser cutting and engraving, optical communication, medical surgery, holography, and 3D printing. Next, the light sources of lasers. So the light produced by a laser depends on an active medium used inside the laser. The following are the common laser light sources: gas lasers, diode lasers, solid state lasers, fiber lasers, semiconductor laser, excimer lasers, free electron lasers, chemical lasers, dye lasers, and X-ray lasers. We can see these lasers one by one. So first of all, gas laser. So the feature of this gas laser is the active medium is a gas mixture and it produces high coherent light. These gas lasers are used in laser printers, engraving machines, holography, and optical experiments. The example for this is helium neon laser, carbon dioxide laser, and argon laser. When an electric current is passed through the gas, it emits photons and it creates broad spectrum of light. The next laser is diode laser. Here the active medium is a semiconductor junction and it is small size and it consumes low power. These diode lasers are used in laser printers, barcode scanners, optical communication, CD, DVD, and Blu-ray drives. These semiconductor diodes are compact and it is efficient light sources used in this laser technology. Here they operate by passing a current through a semiconductor material which emits light due to the recombination of charge carriers. Next one is solid state lasers. Here the active medium is a solid crystal. It produces high power laser beams. These solid lasers are used in laser cutting, welding, medical procedures, and 3D printing. The example for this one is ruby laser and neodymium doped yttrium aluminum garnet laser. They can pump by various means including flash lamps, diode lasers, or other lasers. Next one is fiber laser. Here the active medium is rare earth-doped optical fiber. It gives high efficiency and beam quality. This one is used in metal cutting, marketing, engraving, and industrial manufacturing. They often pumped by diode lasers and produce high power, high quality laser beams. Next one is semiconductor laser. These lasers are based on semiconductor materials similar to those used in diode lasers. They are often used in applications like optical communication system and are the basis for many consumer electronics including DVD and Blu-ray players. Next one is excimer lasers. Excimer laser is a type of ultraviolet gas laser that uses a combination of a noble gas like argon, krypton, xenon, and a halogen gas that is fluorine or chlorine as an active medium. The term excimer stands for excited dimer, a short-lived molecule formed only in the excited state. The advantages of this excimer lasers are extremely high precision, produces UV wavelength, minimal heat affected zone, then suitable for micromachining and excellent for delicate biological tissues. These are the gas lasers use a combination of noble gases and reactive gases to produce a powerful short wavelength ultraviolet light. The disadvantages of this excimer lasers are high operating cost, complex gas handling system, and it requires regular maintenance, then limited gas lifetime. Next one is free electron lasers. A free electron laser is a laser that generates coherent electromagnetic radiation using a beam of high speed free electron moving through a periodic magnetic field called an undular or Wrigler. Unlike conventional lasers, FELs, that is free electron lasers, do not use atoms, molecules, or crystals as an active medium. They are incredibly versatile as a wavelength of the emitted radiation can be tuned across wide range. The advantages of this free electron lasers are very high power and intensity. Wavelength can be turned over a wide range. No conventional laser medium required. Can generate radiation from microwaves to X-rays. Then high beam quality. The disadvantages are it is very expensive, then large and complex setup is required, requires particle accelerators, then high maintenance cost. Next one is chemical laser. Chemical laser is a laser in which the energy required for a laser action is obtained directly from a chemical reaction. The chemical reaction produces excited molecules which emit laser radiation through stimulated emission. The characteristics of these chemical lasers are very high power output, continuous wave operation is possible, it is a high efficiency and suitable for large scale applications. Then the advantages are extremely high power levels, direct conversion of chemical energy to laser energy, it's high efficiency, it is suitable for long duration operation. Some of the disadvantages are it requires hazardous chemicals, complex handling and storage systems, large equipment size, and high maintenance cost. Next one is dye lasers. These lasers use an organic dyes as a gain medium. Here the active medium is an organic dye solution. The wavelength can be tuned over a wide range. Then the application of this dye lasers are spectroscopy, scientific research, medical applications, etc. Next one is X-ray laser. These lasers generate extremely high energy X-ray radiation. An X-ray laser is a laser that produces coherent electromagnetic radiation in the X-ray region of the spectrum. The wavelength typically between 0.01 nm and 10 nm. Unlike these conventional lasers that emit visible infrared or ultraviolet rays, X-ray laser generate extremely short wavelength and high energy radiation. These are used in the field like material science, biology and chemistry. Next one is optics. Here we are going to see about the deflection and modulation of laser. This optics plays a crucial role in the manipulation and control of laser beams. The laser beam deflection is a process of changing the direction of the laser beam from its original path using optical or electronic devices. Then modulation. This laser modulation is a process of varying one or more properties of laser beam to carry information or control its output. So now we can see the methods of laser beam deflection. These are mirror, prisms and beam splitters. So first of all, mirrors, that is commonly used to deflect laser beams. They can be a flat and curved, and also it can be used to steer the beam in a desired direction. Next one is prisms. Prisms are optical elements with a flat polished surface that can be used to deviate the path of laser beam by refraction. Next one is beam splitters. These beam splitters are the optical devices that split the laser beam into two or more beams. They can be used for both diffraction and to create multiple beams for a single source. Next one is modulation. Here we can see the types of laser modulation one by one. First one is acousto-optic modulators. So these acousto-optic modulators are used for the interaction of a sound wave with the beam. By applying an acoustic wave to crystal, the refractive index changes, allowing for modulation. Next one is electro-optic modulation. It is used for an electric field to change the refractive index of a crystal, which in turn modulates the laser beam passing through it. Next one is polarization modulation. By changing this polarization state of laser beam, you can effectively modulate these properties. This can be achieved using various optical elements like polarizers, wave plates, and pocket cells. Next one is spatial light modulators. These are the devices that can modulate the phase, intensity, or polarization of the laser beam at different points across its cross section. They find applications in beam shaping, wavefront correction, and holography. Next one is frequency modulation. This involves changing the frequency of laser beam over time. This can be achieved using techniques like direct modulation of the laser diode or by an external modulator. Next one is intensity modulation. This involves changing the intensity of the beam over time. This is commonly used in applications like laser communication systems. Next one is amplitude modulation. This is a specific type of intensity modulation where the amplitude of the laser beam is varied according to a modulating signal. Next one is phase modulation. This phase modulation involves changing the phase of the laser beam in a response to a modulating signal. It is commonly used in applications like coherent communication systems. Next one is frequency shifting. This involves changing the frequency of the laser beam used in applications like light detection ranging or distance measurement. So that's all about this. In the next video, we can see the next topic. Thank you.